Modular arithmetic equations have applications in cryptography. They're also kind of wild and fun. In this problem, we're trying to prove a condition under which the equation a times x mod n equals 1 has a solution for the unknown x. What does this mean? A times x mod n represents the remainder that we get when we divide a times x by n. When does that remainder equal 1? We're assuming that n and a are positive integers with n greater than 1. We're letting d represent the GCD of a and n, the greatest common divisor. We're trying to prove that this equation has a solution for x. If and only if it's a two-direction proof, d, the GCD, equals 1. In that situation, we say that a and n are relatively prime, also called coprime. It means they have no prime factors in common in their prime factorizations. An important note for applications is that this condition is what determines whether a positive integer a has a multiplicative inverse in mod n arithmetic. When a times x mod n equals 1, we say x is the multiplicative inverse of a mod n, because when you multiply them, you get the multiplicative identity. Moreover, x will be the unique multiplicative inverse of a if we additionally require that x is between 1 and n, possibly equal to 1, but not equal to n. Before doing this if and only if proof, let's consider a couple examples and also write down a couple facts that we'll need. For a couple examples, first consider 1 times x mod 4 equals 1. Is there a solution for this? Evidently, according to this condition, since the GCD of 1 and 4 is 1, they are relatively prime, there is a solution. Pretty obviously, the solution is x equals 1. 1 times 1 mod 4 is what? Well, 1 times 1 is 1. What is the remainder that I get when I divide 1 by 4? It's 1, because 1 equals 4 times 0 plus 1. The remainder is 1. How about 2 times x mod 4 equaling 1? 2 and 4 are not relatively prime. There should be no solution for x in this case. And that's true. No matter what x is, 2 times x will be an even number. When you take an even number and divide it by 4, you will not get a remainder of 1. How about 3 times x mod 4 equaling 1? 3 and 4 are relatively prime. There should be a solution to this. If you think about it, and if you want x to be between 1 and 4, possibly equal to 1 and not equal to 4, you'll see that x equals 3 fits the bill. 3 times 3 is 9. 9 divided by 4 has a remainder of 1, because 9 equals 4 times 2 plus 1. For this example, both 1 and 3 are their own inverses. We could even write 1 inverse equals 1 and 3 inverse equals 3. This does not look so strange in ordinary arithmetic, but this looks strange. Usually, 3 to the negative 1 power would be thought of as 1/3. But in mod 4 arithmetic, 3 to the negative 1 power equals 3. If n happens to be a prime number, then no matter what a is, as long as a is not a multiple of n, there will be a solution for x. For example, 5x mod 7 equaling 1. What is the solution for x here? A little bit of experimentation will help us. Try different values for x. If x is 1, we get 5, but 5 mod 7 is not 1, it's 5. If x is 2, we get 10. 10 mod 7 is 3, still not 1. If x is 3, we get 15. 15 mod 7 is 1, because 15 is 7 times 2 plus 1. The remainder we get when we divide 15 by 7 is 1. X equals 3 is the answer here, and we could write the inverse of 5 equals 3 in mod 7 arithmetic. To do the proof, what theorems do we need? The first theorem that we need is called the division algorithm. It's kind of a funny name. Algorithm means procedure, but this is really a theorem. It's a mathematical fact. Given any two integers a and b are elements of z, the set of integers, with, okay, let's restrict ourselves to positive values of b, then there exists unique, this backwards e means there exists, and the exclamation point means unique here, it doesn't mean factorial, integers q and r for quotient and remainder such that a equals b times q plus r And the uniqueness is with respect to the fact that the remainder must be between 0 and b, possibly including 0, but not including b. This is essentially formalizing the arithmetic you did back in 4th and 5th grade. What is the other fact that we need? It's related to something called the GCD is a linear combination theorem. GCD is a linear combination theorem. It's really a corollary of that more general theorem. We're given two integers, a and b. We can say that a and b are relatively prime. GCD of a and b equals 1 if and only if it's a two-direction theorem. There exists integers s and t such that a times s plus b times t, a linear combination of a and b, equals 1. These are the two theorems that we now need to do the proof. Remember, we're trying to prove an if and only if, two directions. That means there's two things to prove. We start by assuming that ax mod n equaling 1 has a solution for x, and we try to prove that d equals 1, d being the GCD of a and n. And the second thing we prove is that if d equals 1, then this equation has a solution. Let's prove the rightward direction first. Proof, the rightward direction. Suppose there exists an integer x such that ax mod n equals 1. There is some integer x where this is true. When I take a times x and divide by n, I get a remainder of 1. Well, what does that mean? That means, well, think about the division algorithm here. There exists a q in the integers such that a times x equals n times q, q is the quotient, plus 1. This 1 fulfills the uniqueness in the division algorithm. It is the remainder because we're assuming n is greater than 1. And indeed, our remainder that we have here, 1, is less than n. N is playing the role of b. But now we can take this equation and rearrange it. We can subtract n times q from both sides, and we can write a times x plus, let me write minus nq as negative qn equals 1. Or in fact, we could also think of this as n times negative q. This equation now fits this equation here with x equals s and negative q equals t. Therefore, by this if and only if up in this theorem here, this implies that the GCD of a and n equals 1. We are done proving the rightward implication. Now let's prove the leftward implication. Suppose d, the GCD of a and n, equals 1. Once again, we start by using this fact. We essentially just work backwards now. Because this GCD is 1, we can use this fact to say there exists s and t, integers s and t, such that as plus nt equals 1. But rearranging this, we get a times s equals n times negative t plus 1. Once again, 1 is less than n because n is assumed to be greater than 1. And this means that a times s mod n equals 1. In other words, the original equation, a times x mod n equals 1, has a solution. We're done. QED. Having multiplicative inverses in mod n arithmetic is important for applications like in cryptography, and this condition tells us when that happens. Thanks for watching.